G'day chemistry students. In this video we're going to be covering dot points 3.2.5, 6 and 7. In this video we're going to be introducing some calculations that we can do using these things called reduction potentials. Let's get into it. So first off, in your data sheet on the third page you have a list of reduction potentials, and so we've been looking at redox reactions in class, and this gives you a little bit of a list of a few different kinds of reduction reactions in particular, and you're given the potentials of each of those reduction reactions. So for the reactions that are on the top, you have a bunch of voltages or potentials that are highly negative, meaning that there is a very low reduction potential. What that means is if you have a low reduction potential, the reaction itself is going to be very, very, very resistant to reducing. So, for example, if you have potassium as an ion, it's very unlikely to take up an electron and reform back into a potassium solid. In this list, it has the lowest reduction potential and is the least likely of anything listed to reduce. Conversely, the things down the bottom have really large potentials. What that means is that the reactions down here, the reductions that we see here, are very likely to actually happen. And so what this sort of acts as in this list here is its own reactivity series. You'll notice that there are lots of metals, certainly in the top half of the reduction potentials, that follow a very similar, if not identical, pattern to some of the metals that were listed in our reactivity series previous in these slides. Now, there are some other non-metals on this list as well. They do have reduction potentials, and a lot of the non-metallic parts are more likely to reduce. The potentials are there mostly for comparison. You probably won't find that a lot of reaction in the scope of this course will use those reduction potentials, but I will teach you how to use any of these equations anyway. So let's get into some application for doing a calculation with a standard reduction potential. We're going to look at a galvanic cell that we've already produced in class, and in this reaction we have zinc solid parting with its electrons to form zinc ions, so that's the oxidation component, and we also have copper gaining electrons to form copper solid, which is the reduction part. Now, looking at our reduction potentials, what we can see first is that the zinc is a lot less likely to reduce, and the copper is much more likely to reduce, and that's based on the size of the reduction potentials there. And this makes a lot of sense. We already allocated our zinc half cell as the part that was undergoing oxidation, and the copper cell with the part that was undergoing reduction. Now, we can actually calculate the voltage of this reaction in a galvanic cell. We can calculate its E naught, or the potential of the entire reaction, or the potential of the cell. And the way that you can calculate that is by taking the E naught, or voltage value, for the reduction of the cathode, and the E naught for the reduction of the anode. So if we subtract those two numbers, here we have 0.34, which is the E naught for the cathode, taking away the reduction potential for the anode, which really results in an addition, and that leads to the E naught of the cell being 1.10 volts. And that is actually the theoretical value for a simple galvanic cell involving zinc oxidation and copper reduction. Now, I want to show you a slightly different method for undertaking one of these standard reduction potentials calculations. I find the first method to be a little bit confusing. I guess when I was learning it didn't make all that much sense to me, but there is another strategy that you can use in which you more focus on what's reducing and what's oxidizing. Now, in this equation, we still work with both reduction potentials for both half cells. Here we have copper and silver. In this instance, the copper is going to be oxidizing because it has the lowest reduction potential, and the silver is going to be reducing because it has the greater reduction potential. Now, what I can actually do is write out an oxidation potential instead of a reduction potential for the half cell which is going to oxidize. So before we said just a second ago that the copper is going to be oxidizing, what that means is that I can reverse the sides of my equation here. So I'm going to put my copper solid on the left and my ion and electron on the right. And here I've effectively written out an oxidation reaction going from reactants to products. Now, when you flip the reactants and products of a reduction or oxidation equation, what you end up doing is flipping the polarity of the overall potential. So if I have a potential for reduction for copper of 0.34, its potential for oxidation is actually negative 0.34. So I've written that there. We're going to be using that in a second. And what we've also got here is the reduction potential for silver, which is just 0.80 volts. Now, if you're going to write a net ionic equation for this reaction between copper and silver, something to note is that the electrons must be balanced at the end. So what I've had to actually do to write out my net equation like it is down the bottom is double the amount of all of the silver components, reactants, and products to make sure that the electrons balance on both sides. And this comes back to our theory that we were looking at with redox, in which the number of electrons have to be accounted for as per the law of conservation of mass. What I will note in particular, though, and this is the important part, is that in both of these equations here, doubled or not, the potential remains the same. So mathematically, when we have to change one or both of our oxidation and reduction half equations, we have to multiply them by some sort of factor. The potentials themselves never change. And that's important when we end up doing the math for the potential of the entire cell. But in my method, rather than doing a subtraction between the reduction of the anode and the cathode, here I'm going to be adding the E0 for reduction to the E0 for oxidation. So in this case, that's going to be 0.80 plus negative 0.34. And that results with a potential of 0.46 volts at the end. I've also combined both equations that have been balanced by the electrons to write up a net ionic equation to best represent the galvanic cell that we have present and its voltage. Thank you very much, everyone. Now, in the next lesson, we're going to take these concepts a little bit further and start to actually predict some chemical reactions using our reduction potential. And in those predictions, we're going to be focusing on whether or not the reaction is actually able to occur. But until then, have a good one.